All right, let's talk about some stuff. We got a lot to talk about today. So, along with multiple correlation, we can also think about different ways of considering how things correlate in the same way that we talk about things in multiple regression. So we're used to thinking about this typical Pearson correlations, oftentimes referred to as zero order correlations. When you start comparing them to these other ones, it just means that there's the correlations between two variables with no other restrictions, just how much do they correlate. As we've seen, we talked about slopes in a different way, where now with multiple regression, slopes represent how much one variable predicts another while removing other variables from the equation, like being able to control for other covariances. That's where this comes in. This advanced correlation stuff is talking about, we can actually look at correlations in the same way we do the slopes. All right, so let's talk about what that means. So in a regular correlation, typical correlation that you've seen a whole bunch. This thing, by the way, is called a Ballantine. I don't know why it's called that, but that's what it's called. It's showing this sort of overlap. You have two predictors, x1, x2, and you have y. And then the parts in here are showing the percentages, like the r squareds, that each sort of variable overlaps with one another. So one of the things that start to get interesting about this, we look at regular zero order correlations. You can see if you look at the correlation between x1 and y, it's both, like it's the overlap, it's where x1 sort of overlaps with y. It includes both of these sort of sections, this A and the C section together. It's fine. And we bring in x2, we can look at how x2 correlates with y. Well, now it's also including this C section, right? And this B section as well. So C is getting counted twice there, right? So the C twice. You start to see why with correlations, not correlations, with multiple regression, this becomes problematic. We don't want a slope between x1 and y and x2 and y to both include this same C because, well, it's sort of overlapping between the two variables. It doesn't show a unique relationship between either of the x's, so we typically tend to remove this. The bigger C gets, the more problematic it is, because as x and y as x1 and x2 try to predict y, more and more gets removed. So we want to try to keep this C section, this C portion here, as small as possible, and having A and B be as large as possible. Right? So that's the issue. So how do we deal with this C equation, this C variable? Not variable, but the C portion of the overlapping variance. All right, so one way is something called a partial correlation. So a partial correlation is when we're going to look at the ratio of, like, the proportion of y that we're looking at in a r squared or something is going to actually take a slightly different form. Because if you look back here for a second, this portion, this a plus c, it's the proportion of all of y, right? So we're looking at basically a plus c over a, b, c, and e, like all this stuff together, because it's basically just what proportion of y is a and c explaining. All right, well, partial correlation looks at it a little differently. It says, all right, we got a correlation between y and x1, but we want to remove the influence of x2 from that equation. But we want to remove the x2 influence from both x1 and y. What does that mean? Well, as we remove this, we're going to say, all right, well, x2 explains this chunk here, this portion here, right? So that part gets removed. But I'm going to remove it from both of them. So this whole thing gets removed, not only from, so like this all gets removed too. So like we're removing everything that where x2 and x1 correspond, and where y and x2 correspond. So all that stuff's getting removed. It's getting removed from both. So how do we look at the proportion in which x1 explains y? Well, all that's left then is this a variable, this a portion, and y now has this whole chunk removed. So y, what's left over in y now, is everything else, which is just A and E. So the R squareds now become A, portion A, over just A plus E, because that's what's left of Y. That's why it says it's basically the correlation between the Y residual, what's left of Y after X2 is removed, and X1 residual, which is what's left of X1 when X2 is removed. All that's left is A, and then A plus E for all of Y. That's what's left of Y. And we get that correlation, and it tells us how much X1 and Y are correlated with X2 removed from both X1 and Y. We can do the flip side if we want to do it for, if we want to know how much X2 and Y are correlated, well, then this section remains. Okay. We're going to look at how much X2 and Y are correlated. This section is going to stay in there, but we're going to remove this section, right? Because we're moving X1 from Y now. What's left then is B over B plus E. So this is the portion, this is what's left over in Y. This is the only portion of Y that X predicts or X overlaps with. Okay. When you see a partial, something called a partial correlation, it's been controlled for by, we're actually removing overlapping variance to look at the correlation between two variables. So it's X1 and Y, removing all other X's from the equation, from both of X1 and Y, and looking at the correlation that way. We'll see a little bit of this in the lab, because there is a partial correlation sort of thing we can do in Jamovi, so we can check it out and see how that compares to a regular zero order correlation. Let's talk about then what is a semi-partial or a part correlation. Now, semi-partial and part are two names for the same thing, depending on where you look. Sometimes they're called semi-partial correlations, sometimes they're called part correlations, but they're the same thing. It's not two different correlations, it's two names for the same kind of correlation. So what's the difference? So look here. This one's Y residual, like the leftover of Y, correlated with the leftover of X1. This one's all of Y correlated with just X1 residual. Because what we're going to do, what's sort of hard to draw here, we're going to remove the influence of X2 from X1. Right, so this is going to come out. Right. But the portion of Y, where the C is, does not get removed. It's just we're removing X2 from X1, but Y is left completely intact. Okay. Right, so how much does Y, all of Y, relate to the residual, the leftover of X1? Well, X1 only contributes A. A is the size, the overlap between X1 and Y that's unique to X1. But we're going to look at that proportion of variance relative to all of Y. We're going to leave Y completely intact, which is why it's A, B, C, and E are left alone. And then for X2, it's just the reverse. B is the only part that X2 uniquely contributes. And we're going to look at that in proportion to A, B, C, and E. What's interesting about these two is that the actual portion of overlap is the same. This is A, this one's B. This one's A, that one's B. It's just what we're considering it relative to. For partials, we're considering it relative to only what is left of Y, the Y residual. For parts or semi-partials, we're looking at the proportion relative to all of Y that's left over. So X2 is only removed from X1. Which one's going to represent a larger R squared, a larger proportion typically? A partial or a part? Y partial. Because the denominator is smaller. Exactly right. Look. So here I'm only dividing by, I'm only looking at relative to what's left over. A and E is a lot smaller area, a lot smaller portion relative to A, B, C, and E. So I'm taking the same unique overlapping portion, A for X1, relative to all of Y, which means this is going to typically be a smaller number. I say typically because there are cases where that's not true, and it's beyond this course, things like suppression and other things that go on with multiple regression. But it is possible, but typically, more often than not, that will be true. So here's the other question after you. Which one of these, the partial or the part, is most analogous to a slope? So what does a slope do? Slope is how much x1 predicts y, removing the influence of all the other x's from x1. They don't remove it from y. They don't adjust the y. They only adjust other x's. So which one is it more like? It's more like the part correlation, exactly. Semi-partials and slopes are very similar. If I want to calculate a correlation that has a very strong association or is analogous to a slope, I'm going to calculate a part correlation, because that's going to tell me how much x1 correlates with y, not predicts, but how much it correlates with y after moving all their x's from x1. Okay. So B's and semi-partials are very similar. B is the amount of change in y for every unit change in x, while controlling for other x's on xi. Semi-partials or parts are measures of the relationship between y and xi, controlling for other x's on xi. So this is just sort of in writing what we just sort of mentioned a second ago. B's and semi-partials are very similar. Now, another way to think about how the variance gets affected is in looking at sequential analyses, and why sequential analyses are important. That if you have variables that represent things that are more important, you should really utilize that and actually allow for variables to assume more variance if they're more important. So if we assume that x1 enters first, so if x1 comes in and enters the equation first, what happens is x1 is allowed to explain all of A and C. Right? It gets credit. So before, when the problem with standard regression is that when there's this overlapping part C, we don't know what to do with it. So we just leave it out. It never gets to contribute anything to the prediction. It does sort of holistically, and like in terms of the F, like the entire thing gets counted, but in terms of each individual predictor, C doesn't get counted by either x1 or x2. Neither one of them get to take credit for it, unless we do a sequential analysis. So as x1 enters first, it gets credit for A and C. It gets to have that whole area to itself. And then as x2 comes in, x2 simply adds this portion, and we can see, okay, well, x2 was able to add this additional portion on top of x1, but x1 initially got credit for this C here. So x1's allowed to predict full force, allowed to use its full ability to predict, and x2 just gets credit for what it can add. Okay. So the partial correlations in this case would be, if we're looking at partial correlations, when x1 enters the model first, the partial correlations would look different. It's going to be A over C, right? Because and then x2 removes from y, but not from here, right? So A, C, and E, so now gets a larger sort of portion. And the part correlations would look sort of the same, but the difference is x1 gets to take credit for both A and C, where in the previous versions, it only got credit for A. Whether it was partial or parts, it only got credit for A. Now it's getting credit for both A and C instead. X2 is unchanged because it's having C removed from it already, so it doesn't make a difference when it enters second. So this is sort of why we're deciding what to do with C by adding in variables first in the model as they go in sort of sequentially. So we've mentioned the multiple correlation multiple times, and I think I've mentioned sort of briefly what it is and how it's computed. But so R, when we talk about capital R, right, is the multiple correlation between multiple x's and a y. So we're typically used to thinking about correlations between two variables. Correlations are often seen as sort of being bivariate. They're just how much the two variables relate. So now we're designating one variable as an outcome. We have a variable y, right, that is our main outcome variable. And we want to know how much a set of x's correlate to that y. And then, we got to think, how is that computed? It seems like it must be rather complicated to compute this multiple correlation. So the way that works is I want a multiple correlation between y and say x1 and x2, or x1, x2, x3, x4, how many x's you have. Well, the multiple correlation between a single y and multiple x's is simply the simple correlation between y and y predicted. And the reason why that is because y predicted is the part of y that's predicted by the x's. We already established that we can combine the x's together and form a predicted variable, this y predicted, and that has some predictive ability, assuming, actually, even if it doesn't do a very good job, it's still going to have some multiple correlation. It may not be very large. We've already established this relationship. We've already established that x's can join together to predict this y predicted. So all we gotta do is just figure out the predicted values, correlate those predicted values with the original values, and that is our multiple r squared. So if you're looking at the Ballantine here, the portions of A, B, and C, but only C one time, right? So the multiple correlation is going to tell us that really the multiple correlation squared. Okay, big R squared is going to tell us the proportion of variance in this overlap. How much x1 and x2 overlap with y. But again, it's only counting C one time, not twice. This is something then, like Jamovi, you can test. I think we might have done that last time. I don't remember if we did it or not. Could have. I guess I could check the video. If you save the predicted scores, you can simply then run a correlation between the y's and the y predicted, and you'll be able to capture r, or r squared. Oh, so when I'm saying portion, like this, the section that I had marked, this portion here, this corresponds not to r, but this is like big R squared. This is the percentage of overlap between the x's and y. So the Ballantine really is representing the percentage of overlap, not r, but r squared. As we look back, I think I said it. Yeah, that a Pearson correlation is if the r squared is basically the A and C portion, right? This portion of the Ballantine here is just the straight Pearson correlation between y and x1. Where for x2 and y, we take the C and B portions. That portion there is now the correlation squared between x2 and y. And I can even use C and D here to figure out the correlation between x2 squared, right? That would be the portion that they overlap. These are all sort of like percentage of overlapping variance measures, like r squared or even capital R squared. The difference is, if you notice, if I try to take the y and x1 and y and x2 portions, and I can't just add them up, right? Because the correlation between x1 and y is A and C. The correlation between x2 and y is B and C. So if I add those together, it's going to be larger than the multiple correlation. It's going to be larger than this combined portion because we're counting C twice. Where the R, capital R, that's what it says, portions A, B, and C, but only one C, not two. Right? So we can't just add up those two portions because it would be something larger than the R squared. If x1 and x2 are completely orthogonal, like unrelated, uncorrelated, then there would be no overlap here. There'd be no C. C would disappear because you got to imagine these two circles being sort of farther apart or farther away from each other. Then the individual correlations squared, it could be added up to give you the multiple R squared. But again, they have to be completely orthogonal. Oh, like if you want to do if you had a third x. So a third x, right, would come in. It would depend on it. It's going to have some overlap to it, right? So we need like a section. This would have to be like F, right? We need another one here that's like G. Make sense? This could be H. So all of a sudden now, if we're doing that, the multiple R squared is going to be A, C, B, F, G. It's going to be everything that sort of overlaps here. It's just we're only going to count F once, not twice, right? It's in the same way. You can keep doing that with more and more more and more circles, if a predictor is orthogonal, there's a beauty to it, right? Because if it's orthogonal, we can count this without any regard to other variables because it doesn't relate. There's no other overlap. There are no C or F portions where we're potentially counting them twice. It's just one overlapping portion. You don't have to control for other variables. So when you have variables that are unrelated, predictors that are unrelated, it becomes a little easier. You really can just add up the proportions of overlap for each variable, and that will give you your multiple R squared. So that's advanced correlation. Let's talk about some advanced types of regression. So one, we talked about categorical variables before, and we sort of stopped short when we said, all right, well, if I have a categorical variable that has more than 2 levels, I'd have to go to multiple regression. I can't do that in simple regression. If I just have 2 groups like male, female, I can do I can code those 0, 1 or something, or even 1, -1 or some coding mechanism. And I can do that in a simple regression. But as soon as I have multiple groups, I have to sort of break it out. And then there's also moderation, which is a fancy word for interactions, things like mediation, curve estimation. So let's talk about some of these things. Before you do most of these sort of advanced techniques, you want to add in an interaction. You want to look at mediation. You want to look at curve estimation with powers and things. It's advised that you center the data first, and part of that, centering the data is not a bad idea anyway, just because it actually creates a 0 point that is meaningful, and now the intercept actually can have some meaning to it. So what that means is that instead of having, if I have a variable that's out here like this, so here's the mean of x, right? And here's y. So I have a bunch of points going through here, but here's 0 is down here, right? Here's my 0 point. I have all this stuff coming out here. Notice that this 0 point is sort of meaningless. It exists outside of the range of points. It doesn't really make a whole lot of sense. Well, if I center the data, if I take all the points and I take every single point that I have on x and I subtract out the mean, I don't have to divide by the standard deviation or anything to standardize. I just want to subtract the mean. What that does is it moves the y-axis over to where this is. So now all of a sudden y moves here. The relationship remains exactly the same. It doesn't affect the slope at all. But now my intercept value starts to is set at the mean of x, right? It doesn't equal this. It's A now can be interpreted as what y equals when you're at the mean for x as opposed to some artificial y value. So A won't equal the mean of y. A won't equal the mean of x. It tells you what the expected value for x is when you're at the mean for y. So basically saying, like, what does an average person score? An average x person score on y? That's sort of more meaningful than what is some fictitious 0 person score on y way out here. So centering helps to sort of make the intercept a little more meaningful because it places the y-intercept where x equals the mean. It also does some other stuff too to help. It helps to reduce some superfluous multiclinearity that occurs and stuff. There's some other benefits to it, but the main thing is it helps to sort of when you're like cross multiplying variables to get interactions, it helps to sort of to reduce some of the multiclinearity that gets added in because of that. So it's always sort of recommended when you're doing sort of more advanced things, or even just regression in general, it's often a good idea to center data first. Right? So once you do that, we can do, we talked about simple regression can accommodate variables that are continuous and dichotomous, but once you have more than 2 variables, you now have to sort of move on. You need to do multiple regression. You have multiple dichotomies sort of built in. So if you have multiple, say, J categories, so you have a variable that has 5 groups. You maybe looking at ethnicity. You have 5 different groups that you want to compare. Well, you need to then create j minus 1, so 5 minus 1, 4 different dichotomous variables in order to code out comparisons between all those groups. The reason why that's important is we oftentimes assign numbers to categorical variables. We do this all the time. We'll assign zeros and ones and negative ones, or we'll just give numbers to 5 groups, 1, 2, 3, 4, 5. If I just put that variable into a regression equation, it's going to assume that that 1, 2, 3, 4, 5 is continuous, and it's going to create a continuous slope. But that assumes that the differences between, say, 1 and 2, 2 and 3, 3 and 4, all the different numbers are going to be the same. And if something like a category, like ethnicity, it's saying the difference in whatever you're measuring between Caucasians and African Americans is the same as it is for African Americans and Asian Americans. Like, it has some consistency, and the slope means the same at every point. And we know that's probably not the truth. So we then can split those groups up into multiple dichotomies to compare things, and we have to sort of decide how to do that. So we can do that in a couple different ways. The typical approach is either, again, dummy coding or orthogonal coding. There are actually lots of other ones. There's difference coding, Helmholtz coding, repeated coding, all kinds of stuff. But these two are the sort of probably most typical, and we'll just talk about these. If you're interested in other types of coding mechanisms, then you can sort of look them up. With dummy coding, you're assigning one group to be a reference group, right? So it's sort of like they're the control group you're comparing everybody to. And so in this case, whatever group across the two variables, it has zeros on both, is now your reference group. So this one, category 1, is now the reference category. The first variable here is comparing category 2 to category 1. So x1, whatever the slope is going to tell you how much does category 1 differ than how much does category 2 differ than category 1? X2 slope is going to tell you how much does category 3 differ from category 1. But notice I'm taking category 2 versus category 1, and then category 3 versus category 1. So both of them are being compared to category 1. Category 2 and category 3 do not get compared to one another. So there's no comparison between these two categories. They're both being compared to the one reference group. Okay. Doesn't have to be in this order. I could have had the zeros at category 2 and 1 here and 1 there. It would just change what category is the reference and what we're being compared to. But the coding would, you could code it that way, it'd be fine. These are, again, more they sort of correspond or analogous to like t-tests. I'm taking category 1, directly comparing it to category 2. Taking category 1, directly comparing it to category 3. Right? So they're more like t-tests. The values you're going to get are going to be direct differences. Orthogonal coding is the one where we talked about this before, where we're sort of setting up a fictitious zero that's going to sit at the mean, at like the grand mean between the groups, and we're going to compare all the groups to that grand mean. But the way that works gets a little funny. So for orthogonal coding, people like orthogonal coding because they're orthogonal. I can now interpret each of the different slopes without referencing anybody else. The correlations between the predictors now and the outcomes are they're not correlated. So the R squares sort of add up. Everything's sort of nice and additive. It makes everything sort of clean and neat. So here again, you got to think about what 0 is. So 0 is 2 points away from category 1 and 1 point away from category 2. So it starts to become a funny thing where you have to think of it almost like a timeline. Not a timeline, but a number line. So 2, I got 1, 0, negative 1. Okay. So here's my group 1. Here's my, or in this case, category 1. Here's category 1. Okay. Here's category 2. What ends up happening is that we're going to stick this, so that this ends up being the grand mean. So the value for each one of these becomes a little funny to interpret. If you look at the slope exactly, the slope tells me one step. So whatever the number is, the slope tells me how much the slope changes once there, how much it goes away twice here. Because each single unit change in x going from -1 to 0, you change the slope. Going from 0 to 1, you change the slope. 1 to 2, you change the slope. So we can figure out how far apart these two groups are by thinking they're 1, 2, 3 times the slope apart. And it becomes sort of weird to interpret, but typically, if we're using orthogonal coding, we probably don't care a whole lot about interpreting the slopes. We're really more interested in the ANOVA part, and we'll get to that sort of after the midterm. But these kinds of codes are very useful because it will replicate a typical ANOVA that we are used to, like the one way between groups, those kind of things, ANOVAs. So these categories, the slopes don't really matter a whole lot in terms of interpretation. We're more interested in the overall F value. And because they're orthogonal, we can add them up and it becomes nice and neat and tidy. The second category now, notice that 0 is now here. This is 0. And we have that category 2 is 1. Right? So category 2 is coded 1 here. And category 3 is now -1. So this 0 now represents the average between these two groups, and the slope will tell you how far away each group is away from that average. So you can say that each group is 1 slope away from the average, or the groups are 2 slopes apart. These are harder to interpret, but people typically, when doing regression, tend to like dummy codes because they're really easy to interpret. I don't have to do all this weird stuff. 0 represents one of the groups, and then each x tells us, or each slope tells us how far the other groups are away from that one reference. Orthogonal coding becomes more complicated. Let's before we start thinking about, I don't understand, let's look at an application of that real fast. Okay, so I have an example here. If I use, well, here's a fictitious example I've used in another class, and I think it's kind of funny. Let's say I'm trying to treat depression or something, and I use a placebo. Right? I use one of the well-tested, tried and true sort of. This is treatment for anxiety. Yeah. Trying to treat anxiety. So we got placebo, we got Ativan that actually is a treatment for anxiety, and then we got a new drug that I'm trying to put on the market called Screwidol. Okay. And I'm trying to figure out if this works as well as Ativan, better than placebo, and hopefully maybe even better than Ativan. So I have people come in who are anxious, they take the drugs, and we figure out if this works better or worse or the same or whatever. So I need to code this all out because I have 3 groups. I can't just throw like 1, 2, and 3 into a model as a predictor and see if that works out, because it's going to assume that that's continuous. So I have to convert this over to dichotomies. So one way I can do that is through dummy coding, and because I have a control group, a literal control placebo, it makes sense to treat it that way. So with dummy codes, I'm going to use 0s for the control group. And the first comparison I'm going to see if this is Ativan different than the control, and I'm going to leave Screwidol out. The second one, still going to have 0 for the controls. Okay. But now this is going to be 0. This is going to be my reference group. Okay. Let's look at what we find. It tells me, when I do this, it tells me that they're related, right? So there is something about these codes. These codings that we're doing are predicting anxiety, which means there's some differences between the groups on the anxiety levels. Okay, awesome. So I know that that's working. But how do I interpret the codes? How do I interpret the coefficients? That's the main question. So it tells me the intercept is 8. X1 is -0.8 and X2 is -3.2. Go back a second. If what I said is true earlier, because zeros are, I basically have this equation: y predicted equals -0.8 times X1, right, minus 3.2 times X2. and then plus 8. Right, that's basically my equation to predict for predicting scores. So when x1 is 0 and x2 is 0, I would expect my predicted value to be 8. So when both x's are 0, 0 and 0, that's my control group, I expect my expected value, what I expect people to be, the score in this group is 8. If I go back a second, 8 is the mean of, I guess I'm trying to screw this up, 8 is here, is the mean of the control group. How much farther down is Ativan from control? Well, it's 0.8 units below. How much farther down is Curvilinear from control? Right, well, it's 3.2 units below. Well, that's exactly what I got back in my slope. Tells me that x1 tells me that the Ativan group here is 0.8 below the control group. And x2 tells me that the Screwball group is 3.2 below the control group. And each one of these has a standard error, and we can test it. Is there a significant difference between Ativan and control? That's the x1. Well, that 0.8 difference is not significant, right? Not significant at all. But the 3.2 difference between Screwball and control is significant, so we're able to tell not only collectively is there a difference, but the real difference comes in between the control group and the Screwball group. Right? And that's coding this as coding it as a demicoded variable. So just think, again, when you plug this in, we always ask, well, the intercept is the value of y predicted when the x's are 0, right? So x1 and x2 have to be 0. So when is x1 and x2 0? Well, for anybody in the control group, they get both zeros. So my expected value for anyone in this group is going to be 8, which is basically the mean of the group. All right. Let's try this. I'm going to do the exact same thing, just thinking about it as orthogonal coded. Okay. Now here's the main thing down here. Look at the mean. The mean here is 0.333 and 0.33 because there actually are numbers in here, zeros and ones. Here it's 0 because as we add up all these codes, they're going to equal to 0. Everything's sort of perfectly contrasted. So here, this is going to be a little bit different comparison. I'm going to take my control group. I'm going to give it a 2. My Ativan group is going to be 1. This is going to be -1. I'm sorry, these all have to be -1. These are going to all be -1 because we're comparing them all to. Let's see, I must have done something goofy because this is. Oh no, that's right. I see. -1, -1, -1. Okay, so 2, 2, 2, 2, 2. Right, that's 6 2s. That's 12, and then I have 12 -1s, which is why this ends up to 0. The thing about orthogonal codes is that once you sort of cross the line, I'm comparing, I've compared the control group to everybody. Well, I can't now cross that same line again. That group's already been addressed. So the best thing to do then is to make sure that you. Sometimes these things start to dry out a little bit. Okay. Is to then leave it out. So I already used that. So now I'm going to go through and compare the control group to everybody, and then I can compare, say, my Ativan group to my Screwball group directly. Oops, this is -1. So now I get the same kind of prediction. I can do y predicted equals the 0.667 times x1 plus 1.2 times x2, and then plus 6.667. All right, when is x1 and x2 equal 0? That's when y predicted equals the intercept. When is it equal 0? All right, so the equal for 0 here, it's got to be somewhere in between the two of these, right? We need to actually, it's sort of 2 steps down from this group and all this stuff. Well, when they're both 0, when x is equals 0, what you get is the grand mean. So it's a value that doesn't exist in the data set, but it can be computed. If you look here, if we do all the scores, you can figure out the grand mean, but because they're all equal numbers, we can also take 8 plus 7.2 plus 4.8. We can do that. And divide by 3. 8 plus 7.2 plus 4.8 divided by 3 equals, all right, you can see it or not, but the mean becomes, the grand mean of all the scores is that 6.667. So this tells me how much is that group, how much, what is the grand mean for all the scores? Okay. X1 tells me that there is a 0.667 difference for every unit of x from that 6.667. All right, well, let's look at the mean. Look at the mean for, say, for the control group. Okay, the control group is 8. All right, so to get to, starting from 0, to get to the control group value, like if I plug in 2 in here, okay, so if I want to predict the control group score, okay, I'll just plug in the control group score to get my predicted value. That would be predicted value equals, right, this is for 0.667 times 2. It's 2 units, 2 unit shift, right? Plus 1.2 times 0, because the control group has a 0 in the x2 code, plus 6.667. All right. What's 0.667 times 2? 0.667 times 2 equals 1.334 plus 6.667 equals, so this is going to give me an 8.001. Right, so we captured the mean of the control group by simply plugging in its codes for the two x's, because the control group is 2 units above the slope. I mean, sorry, the intercept. What about for Ativan? So Ativan, if I plug in the codes for that, it's 0.667 times -1, right? Plus 1. So this is 1.2 times 1. So those are the 2 codes that Ativan has for its value, plus 6.667. So I can take 6.667 minus 0.667 plus 1.2 equals 7.2, and we're able to recapture the Ativan group's mean, 7.2. Okay, by simply plugging in its codes, it can predict for me the mean of those scores. What about, this is for the control group, this is for Ativan. Let's do it now. The last one, if you screw it all. This is 0.667, also times -1, plus 1.2 minus the 1, right, plus 6.667 equals, now I'm going to take 6.667 minus 1.2 minus 0.667, I get 4.8. Right, so it's able to recoup back to the means, because whenever you have groups like this, you have categories, categorical variables. What you're basically doing when you're doing a regression and you're doing the predicted values, we're going to predict the value of the group's mean, because what we predict for a group, all we know about them is what group they belong to. So my best prediction for them is the average for the group they belong to. That's why we're recapturing back those means, and we can actually use those. You can use the means here, the 8, 8, 8, 8, 8, and then we can figure out the residuals. We can figure out the 7.2s, figure out the residuals. And this just starts in your mind. You start to see that this starts to look a whole lot like an ANOVA. That you have the group means. The deviations around the group means are the within group deviations, within group variance, which here we're calling residual, but in ANOVA we call it within group. Same idea. And then we can also compare the means across the groups. Those are predicted values to the grand mean to get a regression, which in ANOVA we call between groups, but it's all the same stuff. We're doing the same thing, it's just renaming, rebranding stuff, but it's all the same kind of process. We're asking, are the groups different in terms of their means relative to their residuals, relative to the errors that are produced, and sort of assuming everyone's at their group mean. All right, what about moderation or interaction? Well, you can actually figure out, so what is an interaction? I mean, I think that's sometimes like what students find a complicated idea. What does it mean to have an interaction? So testing for moderation can be accomplished by simply cross-multiplying the variables and adding a new variable as another predictor. So first, let's talk about what does it mean by moderation? So oftentimes, we will say we'll have things like this, where we have some y variable, and just for the sake of not using x over and over again, I have some predictor A that I think, predicts y. I have another one B that I think predicts y. And sometimes we can leave that alone. We can be like, all right, that's it. I think A and B predict y, and I want to, control for the overlap between them. Sometimes you'll see that in a picture like this, where we're going to control for their correlation when we predict y, and we're going to see, these are the slopes, like for the two of them. We're going to see how well that relates. Yeah. Okay. But what if I think the presence of A and B together, when they're actually in the same model at the same time, that one may actually change the other one? There actually might be some belief that, A changes how B affects Y, or B changes how A affects Y. So we can bring in something called a moderation or an interaction term that's basically just cross-multiplying A and B. And we can predict y with that and get another slope that tells me if there's an interaction or not. And we still control for the correlation between all this stuff, but we're going to center and everything to try to minimize how much these two overlap with the A times B, because they both contain A and B, so we want to keep that as minimal as possible. And the question though is, what is this thing? What do I mean by moderation or interaction? Interaction, by the way, is more like an ANOVA type term, even though it is used in regression too. And you get more regression, and later if you take more courses, you get to things like path analyses and stuff. The term moderation becomes more in use, but it's the same thing. Does A moderate B? Okay. So what does that mean? Why do I care? What is an interaction? How would you explain an interaction to someone who's never heard of one before? The slopes are parallel to each other. Interaction. So, okay, when you're thinking about it in terms of, I think I know what you mean. When you think about it in terms of, all right, you have a slope. What starts to happen is, if I have, this is sort of the more ANOVA way of thinking about it. I think it might be what you're getting at, where you have like A1 and A2 are my two groups of A, going back to this example. And then I plot out the two B lines, or one B line goes like this, and the other B lines, this is like B1. B1, and then this is like B2. That this indicates an interaction, because For when you're looking at just B, A1, we increase from A1 to A2. But we look at it in terms of B2, we're actually decreasing from A1 to A2. Is that what you're talking about? Between parallel and yeah. So this is oftentimes how interactions sort of are explained, and they're explained in terms of groups and things. So let's give this some context. Let's say this is, you gotta think groups. Let's say the outcome is like, I don't know, this is your sort of, your degree of liking or something, liking of movies. Like you go to movies and you like it. Okay. This is I don't know. Let's see. This is a comedy. This is a horror movie. I think categorical. This is with lights on. And this is lights off. I don't know. Just making this up as I go here. So if you're looking at comedies, right? For comedies, somehow the lights are on. People tend to like horror over comedies. They're actually rating the horror movie better than the comedy when the lights are on in the theater, right? Maybe because when the lights are off, the horror movies are a bit scarier. Comedies are, really all that affected by it. So they like the horror movies less because they're more scary, and the comedy movies more. So the lights on or off, this condition moderates how much the type of movie affects your liking. Right? So A predicts Y, B predicts Y, but there is this A and B difference where A changes how B predicts Y, and vice versa. That's sort of the typical like group-based interaction kind of term. I want you to think about it a little different. So the definition of an interaction is that the interaction between A and B, that this variable predicts variance in Y that either variable do not predict alone. So an interaction is that A and B affect one another, right, in predicting Y in a way that is not captured by A or B alone. So if an equation, we're typically used to seeing a regression equations this way, where it's like Y predicted equals B1 times A plus B2 times whatever B is, and then plus I know it's just confusing with lots of A's and B's. The little b's are slopes, little a is intercept, big A, big B, okay, is the two variables. And I can just do this, but there may be some of the residual, right, maybe left that you could have explained, right? There may be something there that you could have explained a little better, because there is an interaction between A and B. Same thing with like lights and movies kind of thing. So I could add in another variable, A plus B2 times B plus B3 times A times B, actually multiply them, plus A. If this is significant, we actually cross multiply A and B, and this is significant, that means that we're able to explain some of the residual by adding in this other sort of moderation or interaction term, that there is something about A and B working together that is doing something to the outcome that A alone or B alone isn't really explaining. And it's sort of like a goofy thing I always think about, like another group-based one, is that you may, if you think some goofy little thing like this, where you give someone either you get ice cream or they get no ice cream. Right? They get no chocolate or they get chocolate. Okay. Right? You'd expect that this group's going to be a hell of a lot happier because getting ice cream and chocolate combined is going to, they're going to, whatever their rating, their happiness feeling is going to be a lot higher. That they're going to sort of add together more than just getting ice cream or getting chocolate could explain by themselves. That somehow the combination of the two of them is going to explain even more, that their happiness is going to be even higher. But if I don't put the interaction in there, I won't be able to explain that additional variance they get by sort of adding them together. That's sort of an additive. This is an additive type of interaction. But I want you to think more of it in terms of regression. Is that is A affecting B, modifying how much B predicts the outcome, and we can test for that as an interaction term, as a moderation term in our regression equation. Okay? We can actually add it in, and if it's zero or non-significant or something like that, means that they're not, that they're actually both predicting pretty well together, separately. They're both predicting and explaining the variance. But if you add the interaction term in there and explain some variance and you actually have a significant interaction, that means there's more going on, that the two of them are working together, right, in a way that either one of them can't explain alone. And that's sort of a quick rundown of that, but we're running out of time. So let's talk about mediation. Mediation is another way of thinking about how variables relate to each other. Sometimes we're sort of locked into this idea that we have one outcome and a predictor, outcome, that's it. One predictor, we can have multiple predictors, one outcome, but there's still just this sort of, there's only two sides of an equation. That, we might have a bunch of x's that predict y, but that's sort of it for multiple regression. However, sometimes we might have an x that predicts another variable, say z, and then that in turn predicts another variable y, and we can have a sort of a chain of prediction. This is called an indirect effect. Why? Because x indirectly affects y through z. You can have both sometimes. You can have direct and indirect effects. That's okay. But the idea is that x predicts y through z in this indirect way, and this is another term for mediation. Right? Does z mediate the relationship between x and y? Is another way of saying, does x predict y through z? Okay? This is more sort of path analysis and other stuff. This is more sort of out of like social psych uses this term more. They both mean the same thing. When you hear mediation or indirect effect, they're talking about the same stuff. All right, so let's talk about how that works and how we would figure this out. Because you can do this through regression. It's actually not too hard. You just got to keep track of some stuff. So the way it works is you're going to get, you have a total effect. The total effect of, say, whatever your predictor is and whatever your outcome variable is. So you're going to have, I guess a different color. You're going to have, say, x, right, predicts, x predicts y. Okay, that's your, without anything else in there, that's your total effect. And we're going to call this total effect, this thing we're going to call path C. C is my total effect. Okay. Now I also want to look at the indirect and direct effects. Okay. So for indirect direct effects, I'm going to have, still going to have my x, still going to have my y. Those two things don't, these are my predictor and outcome variables. They don't change. Okay. This is still going to directly predict y, and that's totally fine. It's just now we're going to have the presence of another variable z in here that we're going to be looking at an indirect effect for, like that. When z is present, this path is no longer the total effect of x on y. It is now what we call C prime. It is now the indirect effect. And this is the effect of x on your predictor on the mediator. This is the effect of the mediator on the outcome. And it turns out that the difference, C minus C prime, the difference between those two things, total and direct, equals to the indirect effect, which is A times B. This path times that path. All right, so how much the total effect changes to the direct effect? Makes sense. It's how the difference is, well, I now have variance or variation stuff going through the indirect effect that's no longer in C anymore. So C, the total effect minus the indirect effect, the total effect minus the direct effect, total minus direct, equals to the indirect effect, A times B. Okay. So the goal of mediation or looking at indirect effects is to try to figure out is X significantly predicting Y sort of via C? Like, is this A times B significant? Is it something substantial? Is it really there? Okay? Is there an indirect effect? You can think of something like this. Like, let's say this is okay. That's a good one. So we got so let's say, how much does anxiety predict cardiovascular disease? And it could be, and Z could be smoking or any number of other health related things like just poor eating habits or other things. It could be that anxiety leads to stress. Right? So let's keep smoking out altogether. So anxiety does predict cardiovascular disease, and that's because stress is the mediator. Anxiety leads to more stress, which can cause a lot of havoc on you physiologically, the stress, and then that stress turns around. And I mean by physiological stress, because a lot of times people think anxiety and stress are the same thing. I mean that your anxiety leads to stress, physiological stress, that turns into cardiovascular disease. So yes, there is an impact of anxiety on cardiovascular disease, but it's through other sort of physiological or health-related things: smoking, eating poorly, poor sleep, all kinds of stuff that you can actually put in as a Z mediator. How do you do this in regression? I know we're a little bit over time, but that's just like a few slides left. Just wrap it up and we're done. Because we don't have as much to do in the lab. I don't think today. It's shorter. 4 steps to establish. There's 2 different ways people do mediation. One is to do this sort of Barron and Kenny style. It comes through social psychology and trying to relate a bunch of variables together in regression. You need to establish that X predicts Y, right? There has to be a total effect, or else there's no point in doing this. You need to establish that X predicts the mediator. You need to establish that the mediator predicts the outcome, and then this is the part that's sort of funky, that Barron and Kenny sort of argued, that you establish that X no longer predicts Y when both X and Z are in the prediction equation. So like they're basically saying that C prime should be 0. That's complete mediation, but it should at least go to non-significant, right? Partial mediation, steps 1 through 3 are the same, but in step 4, C prime is less than C, but it's still significant. That's sort of a goofy, it becomes sort of complicated. So step 1 has to be that X predicts Y. That has to be significant, right? No getting around that. Then you're going to establish that X predicts Z, which is the mediator. Then you got to establish that Z, these all have to be significant along the way. Z predicts Y. And then this is where it gets weird. The last thing you're going to do in regression, because you can't really do, the indirect effect thing, is that you're going to take X and you're going to take Z and you're going to predict Y from both of them. This should still be significant, and this should now be not significant. This really should be 0 for full mediation. It explains everything, right? That's how sort of Ben and Kenny originally wrote this out, as sort of all or nothing. But it sort of got weakened to, okay, well, at least it went from significant to non-significant. That shows sort of mediation. Right? So when you have a regression equation where both X and Z are together in the model, X no longer predicts, even though it did when it was by itself. And that's the sort of Barron and Kenny sort of approach to establishing mediation in these sort of 4 steps. Okay. More recently, even though it wasn't that recent, it's been a while. There's been a shift, and even a shift away from talking about mediation and talking about indirect effects instead, because I don't think it really matters whether or not I have significant direct and indirect effects. That's stuff that people have sort of agreed it doesn't really make a difference. You don't have to have complete mediation to have mediation. You can have partial mediation. You can have some things mediating, some things going directly. So people have developed sort of ways of actually testing out whether or not that indirect effect is significant. So when people start talking about indirect effects, they're talking more about sort of how to establish, like we can compute a z for the indirect effect and figure out if this is significant or not. These pieces all come from A and B or from those pieces. Remember, if you think x to y through z, this is A, this is B, this is C prime. So you're gonna do all the steps, the Bernoulli steps, to compute what this A value is. Okay, well, x predicts z, that's A. Z predicts y. When you have z and x both predicting y, you can get the B value here from where z predicts y. Each of these are going to have, they're going to give you standard errors for, right? You can have a standard error for each one of those slopes. This is for A, this is for B. And that's actually what's in here. So A times B is simply just taking the slope here times the slope there. A squared is just the A slope squared. B squared is just the B slope squared. This S squared B is literally, they're going to give you the standard errors for this slope, standard error for that slope. All you're going to do is square them to get a variance to sort of plug this in. You can actually compute a so-called test and actually get a test for indirect effects that tells you whether it's significant or not. We can talk a bit about this in lab in just a second. Okay. And one last thing I want to mention to wrap all this stuff up. The last one is sometimes x and y relate to each other in a way that doesn't seem completely linear. We said everything has to be linear. This is a linear regression, even in multiple regression. Sometimes you'll see things like this where the dots will look like this. And sort of a acceleration that occurs, and we want to try to capture that acceleration, but linear regression tells us that we really can't, right? That this is not what linear regression is for. Except we can trick linear regression into doing this, because this is basically just a quadratic, it's a squared acceleration. So we can have y predicted equals, if this is x, right, and this is y, I can put in my x, I can figure out a slope for x, right? Here, I'll even do this, make it color coded. I can put in I can find a slope, looks like the same color. Let's use a different color. I can put in a slope for x. So I can figure out a slope for x, okay? That slope, it's going to give me the best linear slope it's got. So it's going to do something like this. It's going to figure out this slope, probably something like this, okay? It's going to put in its best linear slope it can, and it's going to test that for its significance to see if there's a linear slope there. Then what it's going to do to capture, what we can do to capture that curve is to add in another slope with the same predictor squared. Right? We can actually square all the predictive values, add it in as a separate predictor. So we're going to have x and x squared both in as predictors, which is why it's important to center them. Okay. And we're going to have some kind of intercept. And that will then help to capture this part of the line here. It'll tell us how much linear trend there is. So this will give me how much does linear slope predict? It'll tell us because there is some linear slope there. And then this will tell us how much additional sort of quadratic slope is there. Quadratic. Makes sense? It'll tell me to actually pick up this curve. In a case like this is likely to be significant, this slope, and so is this. There's a combination of both. We could have other scenarios where, for instance, if I have a scenario like this, where, man, you can't see that blue very well. It does not come out super good, but where, you know, the prediction looks something like this. This is X and this is Y. We're going to find that in this case, the linear prediction is going to be really bad, right? It's going to be, best linear prediction I got is 0, right? So there's going to be no linear slope at all. But then when I add in an additional quadratic slope, the quadratic actually will pick this up and be able to give us a some additional quadratic. That this will be significant, and this won't be, because it's almost completely quadratic. But this one's a mixture of linear and quadratic. We're going to get both significant instead of both coming back. All right. Questions about that? I know we sort of at the end sort of jammed out through some stuff, but I will show you at least the moderation and mediation stuff. I'll show you in the lab. We're not going to spend a lot of time with powers, but I didn't want to cover at least that you can actually capture some curves and things, even though it's a linear function. We can add things and tweak the predictors to try to capture some of this curvilinear stuff.